Now we're going to start talking about the properties of limits. So, number one, properties of limits. And by the way, I am recording, and they could hear you. Okay. They can hear me a lot better. They hear just little echoes in the back of the room. Okay. Now, here is the theoretical setup. If the limit as x approaches c of f of x equals L, and the limit as x approaches c of g of x equals k. Now this is just a setup. This is not a theorem yet. Now after you write that down, I want you to take a look at it. How many functions do you see?
2.
You see 2, right? Are the 2 functions approaching the same limit? Are the x values that they're approaching the same? Yes. These are both approaching c, and that's important. Do they have the same limit?
No.
Not necessarily. I'm not going to say no for a fact. L and k could be the same, but they don't have to be. That's why they define them with 2 different variables. If they had put L and L, they would definitely be the same. Just like these 2 c's, they are definitely the same value. Does that make sense? So we're talking about one function that's approaching a limit and another function that's approaching a limit. How do the limits behave when you try to combine things together? That's what these properties are talking about. First property, the limit as x approaches c of b times f of x is equal to b times L. The limit as x approaches c of b times f of x equals b times L. Now, just out of curiosity, how many of you think you understand what that's saying? A few of you. Okay, I expected a few. What I see it as saying is this. Let's change the b to a 2 for a minute. When you take a function and you multiply it by 2, how does it change the graph?
The limit goes up by...
No, don't worry about the limit side. I don't want to talk about limits. I just want to talk about generalities. When you take a graph and you multiply it by 2, how does it change the graph? Does it move it left and right, up and down? Dilates it, stretches it, right? By a factor of 2. So, if the graph is stretched by a factor of 2, won't it make the limit twice as high? Think about it. Yes, it will. So, if this was a half, if the graph is half as tall, it makes the limit half as high.
So just multiplying like the 1.
Right. Now, it looks like you're just multiplying both sides by b, right? And we've been able to do that legally in math for many, many years. But the question is, are you allowed to do it with that limit in the front? And the answer is yes. Even though it says limit right there, you are mathematically allowed to multiply both sides by b. Because in reality, it changes the limit the same way it changes the function. Does that make sense? Okay.
So would you just solve for the limit as it is and then multiply both sides by b? Or is there a different...
There's no solving for the limit. I'll show you in a few minutes how this is used in a real world kind of a situation. Okay? So this is just the way, this is like the behavior of limits. So the limit as x approaches c of f of x plus or minus g of x equals. Okay. Plus or minus. Anytime plus or minus is in some sort of a property, it's because it works for both adding and subtracting, and instead of writing 2 different properties, they just crush it into one. Okay? So, when you add 2 functions or subtract 2 functions, it equals L plus or minus K. So that tells you that if you add the functions, you add the limits, and if you subtract the functions, you subtract the limits. Does that make sense? Okay? So that's how you read that. Number 3. Now that you guys are getting the hang of this, I think you can probably do the third one yourself. I'll tell you the left side, and you can probably tell me the right side. Limit as x approaches c of f of x times g of x. What do you think the right side's going to say? L times K, exactly. If you multiply the functions, you multiply the limits. Number 4. The limit as x approaches c of f of x divided by g of x L divided by k, as long as k does not equal what number? 0. Very good. So, can somebody tell me a sentence without using this kind of lingo, what that means in simple terms?
Wait, what?
Can somebody tell me in simple terms what that means? I'm not quite sure I'm asking the question right. Let me tell you in simple terms what 3 means. If you multiply the functions, you multiply the limits. So what is this one telling you?
You divide
The function. You divide the limits. That's what I'm saying. Does that make sense? Okay. Very good. Last one. Limit as x approaches c of f of x to the n power. What do you think this one would be? L to the n power. Exactly. So what this is showing you is that limits behave the same way as regular numbers do, or regular functions do. You can add them, you can subtract them, you can divide them, multiply them, raise them to powers. Whatever you need to do with it. Okay. For example, let's say we have the limit as x approaches c of f of x is equal to 3. The limit as x approaches c of g of x is equal to -4. And the limit as x approaches c of h of x is equal to 1/8. So now instead of L's and K's, we're actually giving them numeric values. We have some random function f whose limit is 3, another function g whose limit is -4, and another function h whose limit is 1/8. So, part A, tell me what the limit as x approaches c of g of x over f of x would be. Okay? Which of the 5 properties does this letter A look like? Fourth one, right? And it just tells me that I'm supposed to divide the limits. So what should the answer be? -4/3. The end. That's all you do. Okay? Part B, the limit as x approaches c, and this is what's on the quiz tomorrow, of h of x minus f of x is equal to 1/8 minus 3. Okay? What's a quick and easy way to solve that problem? Smile it, exactly. So 3 over 1. 1, 2, 3. So it's going to be 1 times 1 is 1, minus 8 times 3 is 24, over 8 times 1 is 8, -23 over 8. Okay, letter C. I'm going to give you C and D, and I want you to try to do these yourself. The limit as x approaches c of f of x to the 4th power. And then I want you to move this up a little bit, the limit as x approaches c of 8 times h of x. And I'm going to pause it and come around and check and see if you are doing it right. There it goes. All right. We are now going to talk about what is called the sandwich theorem. And I know, yes, you're getting hungry. Also known as the squeeze theorem in some textbooks. I think this is the first true theorem of calculus that we've ever written down. Now what I'm going to do is basically go through and write it down, and then I'm going to explain it, because as I've taught this today, it's been several. Usually it's reading it the first time, you kind of have no idea what it's saying, but after I explain it, it makes a lot more sense. Here we go. If h of x is less than or equal to f of x is less than or equal to g of x for all x in the open interval containing C, except possibly at C itself. And I'm going to wait for just a minute for you to catch up. From what I've written so far, do you kind of have an idea why it's called the squeeze or the sandwich theorem? You see one function that's squeezed between two others? Which function is squeezed between the other two? F of x is. Exactly. Okay, and if the limit as x approaches C of h of x is equal to L, and the limit as x approaches C of g of x is equal to L.
Is the h approaching, is that supposed to be an x?
Oh, I did write an h. Thank you. Good job. Comma. Now that's the whole setup of the theorem. Then the limit as x approaches C of f of x exists, and the limit as x approaches C of f of x is equal to L. Period. Now, probably to a good percentage of you, that looks like I wrote that whole thing in Chinese. You have absolutely no idea what it means. Math is a lot like a foreign language. You've got to translate it. Okay? And like I said on Friday, your professors, a lot of times, and after we've done this year, I think you're going to be better at it, but a lot of times professors will just write that up there and say, okay, let's move on. You all understand it, let's move on. And you're like, wait a minute, I don't understand it. But this is not that difficult. First of all, do you all agree that F is squeezed between G and H? Okay. For all x in the open interval containing C except possibly at C itself. That is kind of complicated. But I'm going to be honest with you. In calculus, as the old saying goes, a picture is worth 1,000 words. So let's draw a picture of what's going on. So draw this first quadrant. Okay. X approaches C. C is like an x value. So on the x-axis, I'm going to put a C. C is an x value, actually. It's not like one. It is. And the L, is the L an x value or a y value?
Y.
It's a y. So I'm up here on the y-axis, I'm going to put an L right there. Okay? Now, the top function, the one that's on top of the other two, is which one?
It's going to be g of x.
G of x. So I'm going to take my pen, and I'm going to draw the g of x function on top, kind of towards the top, but I got to make sure that its limit is L. So I'm going to have this function up here, that when it gets to C, the limit is L. And that's g of x. Okay? And then it says h's limit is also L, and h is the one that's on the bottom of the other two. So I'm going to take my green marker, and I'm going to draw h down low, but its limit has to be L also. I really can't tell the blue from the, the green from the black, sorry. But F you're going to be able to see because it's going to be in red. Okay. Now, since F is always between G and H, what does F's limit have to be at C? It has to go through L, doesn't it? It doesn't have a choice. It could be randomly going all over the place in here, but it's got to go through L. So here's F of x. F of x limit has to be L. Okay. Let me go back and talk about this phrase right here, except possibly at C itself. First of all, F is between G and H. for all the x's. Does that picture show that? That f is between g and h for all the x's in the open interval containing c. In other words, as long as we're close to c, f is in the middle. Except possibly at c itself, and that means there might be a hole at c. That's all that's saying. There might be a hole at c. But can you have a limit if there is a hole? Think about it. Can two sides approach a hole and that hole be the limit? Is that allowed? Yes. So in this case, it's saying there could be a hole, but as long as h and g both go to L, f has to also. Okay? Now does that make sense to you? Okay. What's the good of this? Well, sometimes we may not be able to take the limit of f by hand. There's just no way to do it. But if we know g and h, and we know that both of them go to this same place, we can find where f goes. Or they may not even tell you what f's equation is. How are you going to find the limit of something you don't know the equation of? But as long as you know two things on either side, you can find the limit of this, even if you don't know what the equation is going to be. Okay? So let me show you an example. For example, if 5 is less than or equal to f of x is less than or equal to x squared minus 4 for all x, find the limit as x approaches 3 of f of x. So I have this equation f of x. I don't even know what its equation is. All I know is it's between this function, y equals 5, which is what kind of a graph? What does y equals 5 look like? Horizontal line. And what does x squared minus 4 look like?
Parabola.
It's a parabola. So it's between those two. Okay? So it's somewhere in between those two. I want to know what the limit as x approaches 3 is. Well, if it has a limit at 3, these two should be approaching the same thing, shouldn't they? And that's what we're going to test. So what we're going to do is we're going to take the bottom function first, the limit as x approaches 3 of 5. We haven't ever done that in this class before. What's it going to be? It's going to be 5. Because you have nothing to substitute the 3 into. Let's take the other one. The limit as x approaches 3 of x squared minus 4. Can you do that one by hand? Yeah. 3 squared is 9, minus 4 is 5. So, do we know what the limit's going to be at 3 for f? Yes. So, what you write is this, therefore, get used to that because you're going to do that a lot in this class. The limit as x approaches 3 of f of x, the unknown equation, is equal to what? 5 by the sandwich theorem. And you have to write by the sandwich theorem. Or by the squeeze theorem, either one. Okay? So, both of these lines have to be in your answer. You can't just say it's 5 by the sandwich theorem. You have to show that the bottom function's 5, the top function's 5, therefore it's going to be 5. Okay? Remember I told you in calculus you have to explain y a lot. And this is one of those. That's not that hard of an explanation of y by the sandwich theorem. Okay? Let's do another one. If 4 minus x squared is less than or equal to g of x, is less than or equal to 4 plus x squared, find the limit as x approaches 0 of g of x. I'm going to move this up. G of x is sandwiched in here. So we're going to check the limit of these two and see if they're the same at 0. So we'll do the limit as x approaches 0 of 4 minus x squared. What is that limit going to be? 4. And the limit as x approaches 0 of 4 plus x squared.
4.
That's 4 also. Therefore, 3 dots, the limit as x approaches 0 of g of x. Give everybody a chance to catch up because I know I started flying a little fast. What's the limit going to be? 4 by the sandwich theorem.
You always start with that first equation.
You can use either one of these two. It doesn't matter which one. Yes. Okay. Now, some of you may be thinking the question was asked last period, what if they're not the same? What if these two come out different? You cannot find the limit of f, or you cannot find the limit of the middle function unless these two are the same. Or you could write the sandwich theorem fails. Okay? Theorem fails. Okay? So if this came out 4 and that came out 9, therefore the limit of g of x cannot be found because the sandwich theorem fails. Okay? Any questions before we move on to trig?
What?
To trig. Okay. I will go ahead and say this. I know it'll be on the video, but I'm going to say it to you anyway. I put 2 videos up this weekend that I made at home. One of them is a review of the unit circle, and one of them is the magic hexagon. Okay? I strongly recommend that you watch both of them. They're about 6 minutes long, and you may want to take notes as you go. There was a little bit of problem trying to get the audio and video to sync with each other. I'm still working on that software end of it. These videos, however, are coming out beautifully. Everything is syncing up like it's supposed to. But I would recommend that you go home and watch those to review and refresh your memories on the sine and cosine and the rest of the unit circle. Okay? So let's move on to Roman numeral 3 for today, which is trig limits. We've taken limits many different ways. Algebraically, with calculator, with tables. Now we're going to talk about how to take the limits of trig functions. And I know it's been a while since we've done trig, but you can do this. First of all, the limit as x approaches 0 of sine of x divided by x. If I substitute 0 into the numerator, what is the sine of 0? Okay, 0 degrees is at far right. The y value there is 0. So it's 0 over 0. Do you agree with me? 0 over 0 means what? Keep going. The thing is, though, can you factor that? No. Can you take the conjugate of it? No. Can you smile it? No. What do? Well, this is one of those situations where I'm just going to have to go to the calculator because there's no other way to do this problem. Okay? And this problem is going to be the foundation of the rest of the problems. You don't need to get a calculator out. You can just watch me. I'll do it up here. If you want to get one out, you're welcome to. But I'm not going to spend very long on this. I want to take, and I'm going to type in sine of x over x. And I'm going to do a zoom 4. Now look at this graph. What does it look like graphically the limit's going to be as x approaches 0? It looks like it's 1, doesn't it? But let me push trace. Do you notice that there is no y value? Because it was 0 over 0. But if you trace on either side, look how big, look where they are. 0.998? 0.998? Yes, it's 1. The limit is 1. And so this is going to be we know the answer by looking at the graph and we're just going to accept it. It's 1. Okay, there's no other way algebraically to do this problem. Okay? Now, another one that you need to be familiar with is the limit as x approaches 0 of 1 minus cosine of x divided by x. Does anybody remember what the cosine of 0 is? 1. So 1 minus 1 is 0 over 0. We got a problem with this one also. So let me do this one. 1 minus cosine of x, parentheses, over x, graph. Here goes this one. What does it look like the limit at 0 is? It looks like it's 0. And it is. Because both sides are approaching 0 right there. But if you trace it, it doesn't exist. Okay? So, you need to memorize these two. So make sure you memorize these right here. For 99% of the homework, you're going to need the first one. That's the one I want you to memorize first, right here. Sine of x over x. Okay?
Are you still doing our quiz tomorrow?
No, this is not on the quiz tomorrow. Only what we did at the very beginning of class is going to be on the quiz tomorrow. This will eventually be on a quiz, but not tomorrow. Okay. We're going to take this piece of knowledge and we're going to apply it to other trig problems. Go ahead and write this one down. The limit as x approaches 0 of tangent of x over x. Okay? Now, I bet everybody in here, whether you still play video games as a teenager or you played them as a child, have played a game where you were looking for a hidden treasure of some kind. Or you've been on a website and you found an Easter egg. You know what I'm talking about when I say an Easter egg? It's something hidden that's just kind of a surprise picture or surprise video. What we're going to do is we're basically going to take this problem and we're going to play with it until we find the hidden treasure, which is sine of x over x. Okay? So, what we're going to do is we're going to try to create sine of x over x times something else. That's the whole point of this process. We're going to try to take this and use the trig knowledge that we have to rearrange the problem and create sine of x over x times something else. And then that something else we can find the limit of. Now this limit's going to be 1. Do not get in the habit of saying that sine of x over x equals 1. It doesn't equal 1. It's a graph. But its limit is 1 at 0. Okay? So, that does not equal 1. Its limit is 1, but it doesn't equal 1. Very different. Okay, so for this problem, since I want to turn this into sine, can you think of a trig something that turns tangents into sines? What can you remember? Say it again. Sine over cosine is another name for tangent. Do you remember that? Okay, so let's rewrite tangent as sine over cosine, and then put it over x. Okay, so I want to try to play with this thing until I can get a sine of x over x. Anybody got an idea of what I can do to this to clean it up? What'd you say?
You multiply the bottom x by the top x.
Right, move the bottom up, flip the bottom up. So we're going to put the x over 1, and then flip this up, times 1 over x, equals. Now, let's talk about this for a minute. I'm going to go back to basic math for a second. Does 3 times 4 equal 4 times 3? Does it matter what order you write the numbers down? No. Do you notice here I have 2 things that are multiplied? So is it mathematically okay if I switch them? Is it still going to give you the same final result? Think about it. Yes. So if I switch those 2, I would then have sine of x over x times 1 over cosine of x. Do y'all agree with me? There's my sine of x over x that I wanted. All I did was switch those 2. And those 2 fractions are still equal to each other because it created the sine of x over x that I wanted. Okay? So this has a limit of what? 1. So it's 1 times 1 over cosine of 0. Now I can substitute in the 0. What is the cosine of 0 again? 1. So this equals 1 times 1 over 1, which is 1. And there's the limit. Do you have a question on what I did? Okay, next problem. Limit as x approaches 0 of x squared plus x sine of x over x squared. Okay, I need to take another little detour for a second, talking about what's mathematically legal, because that's one thing we need to know when we're doing calculus problems. Okay, if I give you this problem right here, 3 over 7 plus 2 over 7. When you add those fractions, do you add the numerators, the denominators, or both? The numerators. So this becomes 3 plus 2 over 7, which is 5 over 7, right? Okay. Let me ask you this. Is this a true math sentence, yes or no? Is that allowed? We don't do that very often, but it's allowed, isn't it? Because it's basically this thing in reverse. Agreed? This is something you will be doing a lot in calculus to solve problems because it's a lot easier to do the problem this way. Do you see how this problem looks like this problem right here? You see that? You have two things added on top over a denominator that you can break separately. Now, this works as long as the denominator is a single term. Let me ask you this. Is this true? Can you do this? Is this allowed? If there's two things on the bottom, can you do that? No. Can't do that. Okay? But can you do this? That's true. No, that's false, right? That one was false. What about this one? Is that true or false? That's true, isn't it? When it's multiplication, you can split the bottom up. But when it's addition, you can't. That's not allowed. This is true. Okay? So that's going to come into play later. When it's a single term on the bottom, you can break them into separate fractions. And that's what we're going to do with this one right here. So we're going to write the limit as x approaches 0 of x squared over x squared plus x sine of x over x squared. You've got to put the entire denominator on the bottom of both of them. Okay? So, what does that first fraction clean up to be? That's 1 plus. What about the second one? What can I do to it? Cancel one of those x's. So that x right there cancels 1 on the bottom, and I'm left with sine of x over x. Yay, I found it. Found what I was looking for. So now I have 1 plus, what is that limit? 1. And my answer is 2, and I'm done. Questions? Is this that hard? Not really. You just got to remember your trig. That's the problem. Okay, last problem. Limit as x approaches 0 of sine of 5x over sine of 3x equals. All right. First of all, I got sine, yay, but I've never had to deal with sine of something other than just an x. Am I allowed to pull that 5 out? No. That 5 is stuck there. It's very stuck there. Okay? So, it's supposed to be sine of something over what? What's it supposed to be over? Just an x. But I don't have an x there. So what I'm going to do, would you all stop talking, please? I'm going to multiply the top and bottom by x over x. Because that's going to give an x to the bottom of this sign, and it's actually going to give an x to the top of the other one. So I'm going to switch these two now. And so now I have the limit as x approaches 0 of the sine of 5x over x times x over the sine of 3x. That's looking a little more like what I want. Okay. But I've still got the 5 in there. And that one's upside down. And I'm not sure what that's going to do. So what I'm going to do is actually use the calculator again and play with this a little bit. I know that if it's just a single x over a single x, it's going to be 1. If that's a 5x and that's a 5x, do you think it's going to change the way it looks? Do you think it's still going to go to 1, or do you think it might go to something else? It might go to something else. Let's take a look. So we have, let's do the sine of 5x over 5x. Look at the graph whenever you can see it. Is the limit anything different, or is it still 1? It's still 1. So we've learned that if the top and the bottom are the same, it's going to be 1. So I've got to make them the same, okay? Now what about if it's upside down? What if that sign's on the bottom? Let's see what happens. Let's just do plain old x. X over sine of x. Graph that one. What's the limit? It's still 1. So if it's upside down, it doesn't matter. All we've got to worry about is that what is here and what is on the bottom are the same in order to make the limit 1. Okay? So, let's tackle that little problem. What needs to be right here in order to make this limit equal 1? I need a 5. So what do I need to do to the top? I've got to multiply by 5 also. You can't multiply the bottom of a fraction by something if you don't multiply the top by it also. Okay? What does the top of the other fraction need? It needs a 3. So I need to give a 3 to the bottom as well. Okay? So, what do I have here now? I have the limit as x approaches 0. This right here, that's going to equal 1, isn't it? So I have 5 times sine of 5x over 5x, which I know is going to equal 1 in a minute. The limit's going to equal 1, times, now look at this one. There's the other one. I'm going to leave a fraction bar. I'm going to take care of that 3 in a minute. 3x over sine 3x. That's going to equal 1 also. So what is this 3 really? It's really 1/3. Do the rest of you see that that's really 1/3? Because it's on the bottom of the fraction. So there's a 1 on top, because 1 times 3x gives me that 3x right there. Okay? So this limit is 1. This limit is 1. Bring down everything else. So it's 5 times 1 times 1/3 times 1, which is what? 5/3. And there's the limit. So that one was a little bit more involved than the others. So what did we do? Let's kind of review. We first of all multiplied top and bottom by x over x, and then switched it all around so that each one had an x on either the bottom or the top. Then multiplied in the constants that I needed to create the fractions that I know were going to equal 1, and then I cleaned it up and got the final answer. Any questions at this point?